Dr. Majumdar.
Good afternoon.
So, good afternoon to everyone. In the series of these surveys on differential geometry, today in the afternoon session, we have Dr. Saikat Majumdar from IIT Bombay, and he will uh, deliver his talk on finding matrix with constant scalar curvature. So, without wasting time, I invite my colleague Dr. Ashok Kumar Pathak to chair this session. So over to you, Dr. Pathak.
Thank you, sir. A very good afternoon to all of you. On behalf of NASI TMC Summer School on Differential Geometry and Department of Mathematics and Statistics, I welcome you all to this afternoon session. Today we have the very energetic and young speaker in this session. So today's speaker is Professor Saikat Majumdar. Professor Saikat Majumdar is currently working as an assistant professor in the Department of Mathematics at the Indian Institute of Technology, Bombay. Professor Majumdar did his master degree from Tata Institute of Fundamental Research, TFR, CAM, Bangalore in 2012. He received his PhD degree in mathematics from Université de Lorraine, France in 2016. After completing his PhD, he worked as a postdoctoral fellow at the several reputed institutes like the University of British Columbia, Canada, McGill University, Canada. His main area of research is geometric analysis and nonlinear partial differential equation. He has published several papers in the very reputed international journals, and he has delivered the several talks in the across the world. So today, Professor Majumdar will deliver a lecture on the title "Finding Metrics with the Constant Scalar Curvatures." So without taking much more time, I would like to invite to Professor Majumdar for today's lecture, sir. So over to you, sir.
Thank you. Thank you so much for the very kind introduction, and thanks for the organizers to invite me in this forum and for holding this summer school, especially for our young colleagues. Okay, so a very good afternoon to all of you, and a special hello to our friends. So today I'm going to talk on a very famous problem, and the good thing about this problem is that even it was hard and difficult, it has been completely solved. So the answer is quite satisfactory, and the solution, its solution showed the connection between various branches of mathematics like differential geometry, mathematical physics, especially general relativity, and underlying everything, the partial differential equations and its analysis. Okay, so today will be a survey talk, so feel free to ask me questions, please do not hesitate. And I'll confess from the beginning that this is going to be, the arguments are going to be very heuristic, and I'm not going to be rigorous. I'll introduce many concepts. Some of the things will be new, some may not be new. Okay, so, and also I want to say sincere sorry for not including any of the diagrams. If it was a more conventional talk, I could have, but I wasn't able to include it in my slides. So we might have to use our imagination a bit more. Okay. So let me. The title of the talk, as it suggests, is the Yamabe problem. So Yamabe problem is in honor of the Japanese mathematician Yamabe. So in 1960, he tried to solve the very famous and now resolved Poincare conjecture by variational methods, okay, and by solving a partial differential equation. But there was he published his paper in 1960, but there was a big flaw, the major flaw in his paper, and it was recognized in 1968 and repaired a bit by very eminent mathematicians. And its final solution came by Oba and Richen in 1984. So, but the story of the Yamabe problem did not stop there. So it was only one of the first part, you can say, and it continued, and there has been many subsequent works and things like that. So I work in something generalization of Yamabe problem to higher order of vectors. Okay. So we'll start with surfaces. So for the surface, we have our cases would be manifolds or surfaces which are compact, good topological properties, completeness, connectedness, everything. Okay, And then we have this very satisfactory theory of the uniformization of surface, which I'll prove in this lecture, okay, by PDE techniques, that you can basically deform a compact surface. Okay, so you have a surface, okay, and then you give a background metric on it. It can come from the Euclidean background metric, it can come from something else. But you can basically change it and make the curvature. So on the surface, you have basically one curvature, the Gauss curvature, the curvature equal to -1, 0, or 1. Okay, so roughly the surface can be classified as being like the sphere, okay, or a flat torus, okay, or homogeneous hyperbolic surfaces. So toruses, multiple toruses attached together, connected sums of them, and each having curvature respectively 1, 0, or -1. Okay, so this is a very satisfactory answer, and partly the reason is that we have this topological classification of surfaces. But in higher dimension, the picture is not so nice. Otherwise, you won't be doing all these things. Okay, and it's a lot more complicated. One reason is that there are many more notions of curvature. So the question that we can very naively ask is, can we find constant curvature metrics in higher dimensions or odd dimensions? So can we basically extend this theorem to high dimensions? So the answer is, in some sense, yes. That will be the subject of the Moser problem. Okay. But in higher dimensions, there are basically three main notions of curvatures, and as you might have seen, that the curvature is basically a tensor. Okay. So if you don't know what it is, I would say don't bother. So the curvature can be described by the Riemann curvature tensor. This is the full curvature tensor coming from the Levi-Civita connection. Okay, but this is equivalent to knowing the sectional curvature on tangent planes. So if you know the sectional curvature, you can reconstruct the Riemann curvature tensor. Okay, then you have the Ricci curvature, which in the language of Riemannian geometry is obtained by taking the trace of the curvature tensor with respect to the metric chi. Okay, and then we have finally, so the first two are curvatures, the first two are tensors, and the last one is a function, just a function. Okay, so at each point it's a number. So the scalar curvature function, which is again obtained by taking the trace of the Ricci curvature with respect to the metric. So we have this hierarchy of curvatures, and obviously this is the full curvature tensor. If you know this thing, you know everything. So, but knowing this will be very complicated, very difficult. This is Ricci curvature. It has a fascinating history, as you might know. And now the resolution of the Poincare conjecture by the Ricci flow, you know. And then you have the scalar curvature. So we'll concentrate on the third part in this talk. So basically, the Riemann curvature tensor, knowing the Riemann curvature tensor and saying that it's a constant is very restrictive. So you don't get many much more interesting geometries. That in the sense that if a complete and connected manifold, Riemannian manifold, has a constant sectional curvature, and therefore the Riemann curvature tensor is constant, then it's basically like the model spaces, like it's like a sphere, or the Euclidean space Rn, or the hyperbolic space Hn, or it's quotient by the group isometries. Okay. So basically here the picture is completely known, and it's kind of very restricted. All right. So now, if you focus on the Ricci curvature, this is very, very interesting, and it's a very, very active area of research also now. So, and it has roots in general relativity, the Einstein theory of gravitation. So the Ricci curvature, if you want to say that the Ricci curvature is constant, okay, so recall that Ricci curvature is now a tensor, or you can consider it as a quadratic form on vector fields. So then if it's a constant, then it means the Ricci curvature is like proportional to the metric, okay? Some lambda is some proportional constant. And then such Riemannian manifolds have a very special name. They are called Einstein manifolds. Okay. So in 2 dimension, the picture, as I said, is very, there isn't too much room to for anything else to happen. So any metric is in fact Einstein. And this is a very famous work by, after Einstein gave his theory of gravitation, so David Hilbert, so he made it a more mathematically sound theory, and introduced this variational notion of the Hilbert functional. So what you do is that you consider on the space of, you fix the background manifold M, and you consider a function on the metric. So very roughly, this takes a metric and spits out the value, which is sometimes called the total scalar curvature functional. So you integrate the scalar curvature on the manifold, and you just normalize by the volume. And these dimension quantities are there because because the way the things scale. Okay, but so basically, to find Einstein manifolds and therefore to find metrics which in some sense are Ricci constants is equivalent to find the critical points of this Hilbert function. But finding this is an extremely difficult task. So what we'll do is, instead of considering this functional, okay, over the space of all metrics, so we'll restrict it to the space of only conformal deformation. So we only change the metric conformally. We don't change, in some sense we don't change it in every direction. We just change it in some special direction, which is the conformal direction. Okay. And in this case, the theory is quite suitably developed, and the answer it provides is quite complete. Okay. So this is where we are going to focus. Okay. So the critical points of the Hilbert functional, so this corresponding functional, when we just consider the deformation in the conformal class. Okay, so I'll give the definitions of all these things. Will give us metrics which have constant scalar curvature. So this is our goal, to find metrics with constant scalar curvature, and this is the Yamabe problem essentially. Okay. So I'll not discuss on these things anymore. So I'll just give you some references, some old. These are classical references. So if you're interested, you can look into these references for further information. And everything what I have said here, it can be found in these references. So for example, you can find a lot of related things in this very famous book by Abba called Some Nonlinear Problems in Riemannian Geometry. And then this the very delightful book by Bess, Einstein Manifolds, or you can find more detailed calculations on conformal deformations in this book by Shen and Yao called The Lectures on Differential Geometry, or this book, this is a more PD-oriented book, so called The Nonlinear Elliptic Problems in Conformal Geometry by Alice Chang, or the very definitive survey article on the Yamabe problem, the Lee Parker article, or this very nice survey article by Drouet and Hebe called The Elliptic Equations in All Time. So this is also focuses more on the PD problem issues. Okay. So now let me consider. So what I'm going to do next is to answer this question. So the very first question that I asked, so this one. So I'm going to prove this by PD techniques, and then we'll come back and discuss the higher dimensional cases and end with the Yamabe solution of the Yamabe. All right. So now, what are conformal deformations or conformal transformations? So let's fix for us from once and now on. This is going to be M is going to be a smooth, okay, closed connected Riemannian manifold. Closed means that it doesn't have a boundary, okay, so, and it's compact. So and then any metric which can so by what we mean to say is that the conformal deformation is just the scalar multiple of the original metric. So you take the metric G and you multiply it by some function, let's call it rho, a positive function. Then this new metric G tilde is said to be conformal to G. So this is just at each point. So basically, the G roughly tells us how to measure the lengths and the angles, and this tells us that at each point we just multiply this this metric G with a smooth positive function. Okay, so this amounts to changing the lengths by a scaling factor. So at each point, this is the scaling factor, but this is in general a function. So the scaling factor can change. So depending on, it can be, at some places it can be, the length can be much larger than the original one, and some places it can be smaller than the original one, but we don't change the angles, because when the way the angles are defined, this factor goes away. So conformal transformation, one example of conformal transformation, especially with the Euclidean cases, is that you can translate, okay, you can rotate, or you can change the length without changing the angles. So our conformal deformation of a metric G, so this is more precisely called the pointwise conformal transformation, because we are just fixing the manifold, and we're just kind of finding, just giving it different metrics, keeping the background manifold fixed. So this will be the box G will denote the class of conformal matrix, which is conformal to G, and this is called the conformal class of G. So this is basically rho times G, where rho is some constant positive function, sorry, some positive smooth function. Okay. So the question we can formulate is that, so given a manifold MG, okay, so does there exist a closed manifold always? Does there exist a metric in the conformal class, so G tilde in the conformal class? So the scalar curvature of the manifold with respect to this new metric G tilde is constant. That is, SG tilde is constant. So SG is my notation for the scalar curvature. Okay, so SG tilde is constant. So SG may not be constant, otherwise we don't have to bother about this problem. But can we find a new metric in the conformal class such that SG tilde is constant? So the answer, let me just spoiler alert. So this is yes, and this is what we're going to show. Okay, so now because we are doing a conformal transformation of this metric, so we need to know how the various quantities under described by the metric changes, especially the curvature quantities. Okay. So we need to know the transformation of the scalar curvature under conformal change of metric. Okay, so if you have two metrics, G and G tilde, so this should be SG tilde. So and the corresponding scalar curvatures SG and SG tilde. Okay, then we have this transformation law. Okay, for example, you can find the proof of any of the books I mentioned. Okay. So SG tilde is given by SG divided by this factor rho, and then you have some dimension times the quantity. So this will play a very important role for us. This is called the Laplacian operator, okay, or the Laplace-Beltrami operator, which is given by, in my notation, minus divergence of the gradient. And then you have some other terms which involves the gradient of the conformal factor. Okay. So this is the transformation, which this is the transformation law for under the of the scalar curvatures under a conformal change of metric. So people have found out that we can better describe this by writing this conformal factor in different ways. So conformal factor is just a positive multiple. Okay, so what one can do is that we can take rho to be exponential to phi, where phi is again a smooth function. So this is going to be the conformal factor now. So then the scalar curvatures transforms as follows. So now you have this rho kind of goes here. So you have exponential of 2 phi. And then the scalar curvature with respect to this new metric G tilde. So SG tilde is equal to the SG plus 2 times n minus 1, the Laplacian of this factor, conformal factor, okay, which is given here, and then these quantities. Okay. So now you can very quickly observe that when the dimension n is equal to 2, so we don't have this term. So this term vanishes. And this will, we don't have to bother about these extra terms. Okay. So when n is equal to 2, okay, so this term goes away. So we can rewrite this whole thing as, so this is n is equal to 2. So we have twice of the Laplacian of this conformal factor. So therefore I have this term. And then twice of the scalar curvature, which is in the notation the Gauss curvature, which is kg. The notation for the Gauss curvature is kg, which is 2 times the scalar curvature. And then you have the right hand side term, which is 2 times SG tilde, which becomes kg tilde. And then you have the conformal factor of exponential of 2 phi. Okay. So this is the corresponding transformation law, which relates the transformation of the Gaussian curvatures of a surface M with the conformal matrix G and G tilde. All right. So now this is our equation in some sense. So what you want to show is that we want to change the metric in such a way that the with respect to the new metric G tilde, the scalar curvature, and so the Gauss curvature is constant. So we want to find phi. So if you can find phi such that it satisfies this particular equation with this term equal to constant, then we are done in the 2-dimension case. Okay. But this equation is just not simply an equation. It has topological meaning, which comes from the Gauss-Bonnet theorem. Okay. So we'll come back to this. So for higher dimensions, it's more convenient to change the conformal factor and write it in some other form, so that again you don't want to see the gradient term. So you write the conformal factor as u to some power 4 by n minus 2 times g, where u is some smooth positive function on the manifold. And if you do that, you get a very nice looking equation. And then these scalar curvatures Sg and Sg tilde of the matrix G and G tilde satisfy the corresponding transformation law, which is given by the Laplacian of this conformal factor plus this dimensional things constants times the scalar curvature of the original metric times u is equal to again these same bunch of constant times the scalar curvature with respect to the new metric times this u to power n plus 2 by n minus 2. So we have this new kind of equation for higher dimension. In 2 dimension, we have kind of the right hand side was kind of exponential looking, and here it's some u to some power, which looks very arbitrary now. Okay, so this particular term has a special name. Okay, and why it has a special name, I will tell you. So this this term on the left hand side is called the conformal Laplacian. So the Laplacian plus up to some constants. The scalar curvature is called the conformal Laplacian, and this is given denoted by Lg. So Lg is the Laplacian of u plus this term, okay, n by n minus 2 by 4 n minus 1 times the scalar curvature, okay, and this is the conformal Laplacian. Okay, so we can just rewrite this whole thing here in terms of the conformal Laplacian as follows. So in dimension bigger than or equal to 3, the transformation of the scalar curvatures under conformal deformations are given by the conformal Laplacian. That is, the conformal Laplacian acting on this function u, which comes from the conformal as a conformal factor, is equal to this dimension constant times the scalar curvature with respect to the new metric j tilde times this u to the some particular power, which in this case turns out to be n plus 2 by n minus 2. Okay. So again, the same business. So if you want to find a metric under a conformal change such that it has a constant scalar curvature, we would like to find a nu such that satisfying this particular equation with this quantity being a constant. So, okay, so I'll not describe much the geometrical meaning of curvature. So, but I like to do something with the scalar curvature and describe how it influences the measure, the remaining volume measure. Okay, so if you write, this will be my notation for the volume element. So this double bar denotes the determinant. So G is a metric. So in particular, it's a matrix. Okay, and class and matrix, and we're just taking the determinant of that matrix at each point, and by the definition, it's going to be as well defined. It's going to be positive, and then we have this volume element, okay, which is just the square root of this determinant. And now there is a very classical and very useful expansion of this remaining volume element called the Cartan expansion of metric in geodesic normal coordinates. Okay, you can find again in any of the references I mentioned. So if you fix any point, okay, and around which you take the geodesic normal coordinate, so then this volume element looks like 1. 1 is the Euclidean one, and then the Ricci tells me how much it deviates from being an Euclidean. So you don't see, you immediately have the second order term. So you have xi, xj, the quadratic terms and above. So you don't have the first order terms. So this tells you that the first derivative of this metric g will be 0, and second derivatives are the curvatures, Ricci curvatures. Okay. And then you have the third derivative and so on. So if you integrate this thing on geodesic spheres, okay, so if you integrate this quantity in the geodesic sphere, fixing some r, okay, and then you normalize it, this should be r to the power n minus 1, you have to normalize it, or you write it as 1 here. So this is the Euclidean measure of the usual Euclidean sphere, n minus 1 dimensional sphere. So then basically this kind of tells you, the scalar curvature tells you how much it deviates from being an Euclidean measure. So 1 is the Euclidean, and then you have a minus sign times the scalar curvature times r squared. So again a quadratic one. So there is no first order deviation, it only starts from second order and so on. So you can immediately see that if the curvature is positive, so it's going to be smaller than the Euclidean one, and if the curvature is negative, it's going to be bigger than the Euclidean one. In some sense, therefore, you have, for the sphere case, you get smaller volumes, and for hyperbolic cases, you get the bigger volumes. Okay. So So let me come back to this problem. So what I described in the previous pages can be written as follows. So given a manifold MG, again, closed, smooth, connected manifold, then the problem of any metric G tilde, that is conformal metric, with constant scalar curvature to G tilde, amounts to solving these bunch of equations given the dimension. So find a lambda, so which will tell that the scalar curvature is G tilde is this lambda, and find a smooth find a smooth function on the manifold satisfying this. So sorry, this is for u, and this should be for phi. This again should be u. That if in the two-dimensional case, this is the Laplacian of u, or the corresponding scalar, corresponding conformal factor plus the Gauss curvature is equal to lambda times this conformal factor, and in higher dimension you have the conformal Laplacian on u equal to this lambda, which we kind of desired the new curvature to be, new scalar curvature to be this equal to this constant lambda times u to some particular power n plus 2 n minus 2, and u should be also positive. Okay. So let us see how to deal with these things. So there are again many proofs of this these things, especially for dimension n equal to 2. So I'll just describe one of the proofs. There are many classical proofs. There are many excellent articles. Okay, there are proofs from one of the earliest proofs that one learns is from complex analysis. Okay, but I'll give a more kind of a partial differential equation oriented proof, which will in some sense motivate this corresponding thing for the Inequality problem. Okay. And there is also a very simple, much simpler proof given by the Ricci flow, which in two-dimensional case is very simple to describe. All right. So now, as I said, that what is the significance of this conformal Laplacian, and why we have this special name that there is something called conformal Laplacian is because this reason. So in dimension n equal to 2, the Laplacian quantity is conformally invariant. That is, if you change the metric from G to G tilde by this conformal factor exponential of 2u, then your Laplacian changes in the same way. So it's a conformally covariant or conformally invariant quantity. Okay. So it doesn't matter which metric you're choosing. The functions which will satisfy one property with respect to one of the Laplacians will satisfy the same property with respect to the other Laplacian. So this is in some sense an isomorphism on Laplacians. Okay. So now, but for dimension n bigger than 2, starting from 3 and above, so this is no more true. So the Laplacian is not going to be conformally invariant. So, but the conformal Laplacian is. So in some sense, from the conformal viewpoint, the generalization of Laplacian in higher dimension is the conformal Laplacian instead of just the plain Laplacian. So like the Laplacian in dimension n equal to 2, the conformal Laplacian is also conformally invariant. That is for all conformal factors phi. Okay, you have this conformal Laplacian with respect to this new metric G tilde, that is acting on this conformal factor is giving you some u to some power n plus 2 by n minus 2 with a negative sign, and Lg times u phi, where G tilde is this conformal transformation is a conformal transformation of the original metric G and use the conformal factor. Okay, and this is true for all smooth functions phi. So this also encodes the transformation law of scalar curvatures. Okay. So this is our question coming back. So for dimension n equal to 2, we want to find a lambda, which is a constant, so a real number, and a smooth function satisfying this equation Laplacian u of phi plus the Gauss curvature equal to lambda times exponential of 2 phi in dimension n equal to 2, and then for dimension n bigger than equal to 3, we have this Laplacian, conformal Laplacian acting on u is equal to lambda times u to some power which is n plus 2 by n minus 2. Okay, so this is our goal. So now, I'll just focus on, for the next maybe 10 minutes or so, I'll focus on this particular equation and describe you the picture, which will also motivate this theory, the solution or the approach of the solution for the Inequality. Okay, as you'll see, or you can probably guess that this lambda, this constant, is a conformal invariant quantity. That is, it only depends on the conformal class. If, for any two metrics which belongs to the same conformal class, this lambda is going to be the same. This is an invariant. This is a conformal invariant quantity. So, so basically, two metrics which have the two metrics in the conformal class have scalar curvatures which have the same sign. Okay, and so therefore you can normalize it to being -1, 0, or 1. Okay, so I'll also, you can very easily see this by just integrating it. I'll describe it below. Okay, so in dimension n equal to 2, this follows by integration. So if you integrate on the surface, so integration of the Laplacian on a closed surface, because there is no boundary, this is going to be 0. So you have this integration of this Gauss curvature here, and the right hand side term will be integration of lambda exponential of 2 phi. Okay, and but this is just the conformal factor, all right. And the integration of the Gauss curvature, the total Gauss curvature, is, we know by the famous Gauss-Bonnet theorem, describes the topology of the manifold. So it's a topological invariant. So in particular, it's a conformal invariant. Okay. And for dimension n bigger than equal to 3, this follows because if you again integrated, the the Laplacian term will go away, or you can use the transformation law to show that this is in fact does not depend on the conformal class. Sorry, does not depend, only depends on the conformal. So basically, we can normalize our metrics in some sense, and after normalization, visualize it in a better way. We can just think of that finding metrics with constant scalar curvature by conformal deformation amounts to finding metrics with constant scalar curvature being +1, 0, or -1. So like this case of the model cases of the sphere, or the Euclidean, or the hyperbolic. So all these are locally. Okay. All right. So maybe now let me describe the corresponding theory for dimension n equal to 2. Okay. So given a metric G, we fix a metric G and it's considered as conformal class, and we take a metric G tilde in its conformal class, and we want to find this G tilde such that the Gauss curvature is constant with respect to this G tilde. Okay, and if you recall what I said at the very first line, this is the uniformization theorem for surfaces. Okay, so what you have seen is that we can rewrite and think of this more in terms of differential equations. If we do so, this amounts to solving this particular differential equation. Okay, and if you look at it more carefully, this is a nonlinear differential equation. So so obviously the theory of finding solution is going to be highly non-trivial. And the right hand side here, the nonlinearity is given by some exponential of 2u. Okay, so the first thing we can do is that just integrate this equation. So on integration, as I said, this term will vanish. So integration of the Gauss curvature, so which is the total Gauss curvature, where in the case of surface is only curvature, is equal to integration of lambda times exponential of 2u dvg. But if you remember the change of variable formula from integration, so this is just the integration with respect to this new metric J tilde. So lambda times J tilde. And but the Gauss-Bonnet theorem says that this is equal to a topological quantity, namely 2 pi the Euler-Poincare characteristic. So it turns out that this quantity, lambda times this new volume element, is equal to 2 pi times the Euler-Poincare characteristic. So the total scalar curvature is a topological invariant, right? This is a topological invariant. It only depends on this Euler-Poincare characteristic and nothing else. So in particular, this lambda is going to be a topological invariant quantity, and in particular, a conformally invariant quantity. So the solution of the resolution of the problem, how we're going to describe it, highly depends upon the sign of this lambda. So whether it's positive, that is +1, 0, or negative, like -1. So as you will see, again, this is a very common theme in problems of these kinds, which turns up again in multiple situations, that this case of the positive curvature, okay, like the case like a sphere, is going to be the difficult case, and the other cases are going to be much simpler. But in this case, we can just looking it as a partial differential equation. You cannot solve it always. Okay, or to solve it is very complicated. But you'll take the help of the underlying topology and the geometry of the surface to kind of answer this question. Okay. Okay, if you're interested, you can look at this. This is called the this is related to the Kazan-Warner problem or the Berger problem. Okay, you can see the work by Berger, Moser, Alice Chang, and Yang, and others. So what you can in general ask is that this is a like finding metrics with constant scalar curvature in the case of surface is kind of easy, and it's classical. But you can in more general ask to find prescribe the curvature that can I given a function can that be a curvature or not. So that is the Kazan-Warner problem or the Nirenberg problem of its field. All right, so this was our problem. So because I'll be describing from the variation viewpoint, as we saw that in the very first couple of slides, I said that, okay, Ricci, so Einstein manifolds, that is the manifolds where the Ricci is proportional to the metric, can be found as critical points of functional. Okay, this is a very common theme in variational techniques. Again, so this is a very useful thing to consider. And especially from coming from mathematical physics is the following. So we consider a function on the space of a particular space. So in that space is going to be infinite dimensional in general, space of functions, a particular set of functions. Okay? And then we look at the critical points. So even if I'm describing it very, very roughly, very, very badly, all these things have very, very precise meaning. So here in this particular case, you can find the solutions as the critical points of this functional GHE, which is very typical here. So you can just consider the square of the gradient of the function, or you can just take the L2 norm of the gradient plus this quantity kg, okay, and then this other quantity. So this should be kg, not in unit. So, so this is your equation, and you want to find the critical points of this function. So can you find it? This is the question again. So this is where the we are going from transiting from a more geometric and topological outlook to a more PD and functional analytic outlook. So to even establish that this has a this is well defined, that okay, for some u this doesn't become infinity. It requires significant work, and this was done by Moser. So this is also in some sense called therefore the theory of Moser. So the most natural critical point to look for given any functional is to consider its minimum, right? If you find a minimum, that minimum or maximum is going to be a critical point. Again, in variational points, variational theory, you can look for either minima or maxima. They are basically one of the same up to change sign. Okay. So you can look for in a certain function space the minimum of this, and if this minima is not infinity, okay, if it is not infinity, strictly bigger than minus infinity, sorry, then you can hope to find a minimizing sequence, and then if this is purely from analysis viewpoint, that if the minimizing sequence converges, you are done and you're happy, everything works. But it will not converge for geometric problems like this, and therefore you have this whole notion of concentration and blow-up phenomenon. All right. So we look for critical points of this functional, okay, and then I'll again, if you're interested, you can look it up or you can contact me. But I'll just briefly mention one line. There is a very famous functional inequality called the Moser-Turing inequality, and that establishes that this is actually well defined. So this is something very non-trivial to prove actually. So the Moser-Turing inequality, and by the Moser-Turing inequality, you can show that this quantity here is up to some less than equal to some constant times this quantity. So in fact, your infima are going to be bigger than minus infinity. And infima is a real number; it will exist. So then, okay, you can what you can write is that up to some constant c1 and c2, that this functional is always bigger than equal to 1 minus Euler characteristic, because it comes from here. Euler-Baumgarten characteristic divided by 2 times the L2 norm of the gradient, and then some other quantities. L2 norm of the gradient squared, this is very important, and then other quantities up to some constant c1 and c2. So you can immediately see that this is a well-defined quantity because we have a natural bound by the topological classification that this is always going to be equal to this Euler-Poincare characteristic is at most 2. All right. So if this is strictly less than 2, again, this is from variation viewpoint. Okay, from the analysis viewpoint, you can show that this is coercive and bounded from below, and we can find a minimizer, and we are done. So if this is strictly less than 2, that means by the topological classification, it's not like a sphere. It can be like a flat torus or connected sum of torides, like hyperbolic surfaces. Then this is easy to solve. Okay? But if it's like a sphere, okay, if it is like equal to 2, then it's a sphere up to the topological classification. Then this term kind of becomes 0, and then this only remains minus C1 and C2, and then you don't have any actual bounds on that, and you can establish that. You can always find a minimizer. Okay. Then things can go bad. So unless you are a sphere, okay, things are okay. So if you're below the sphere, in some sense, you're okay. So this is again a very typical phenomena here. Okay, but if you think of it carefully, on the sphere we don't really need to solve it. On the sphere, we have the usual metric, round metric, which has constant curvature. Okay, now the question on the sphere is: are there metrics on the sphere which is conformal to the standard metrics? Okay, which can have some other kind of curvatures, constant curvatures. The answer is no. So when the Euler-Poincare characteristic is equal to 2, then the manifold is the surface is basically a standard sphere. Okay, then you have this very nice result, a classical result of Kuiper from 49, that any metric, okay, which is conformal to the usual standard round metric, which has a constant Gauss curvature up to some normalization that is equal to 1. Okay, so basically it says that if you have any smooth compact manifold, any dimension n, and if the manifold has some topological property, that being simply connected, this sphere is simply connected, and it's conformally flat. I will also kind of tell you what is meant by this conformally flat thing. Then it's conformally diffeomorphic to the standard round sphere. So in that case, the answer is solved. We don't need to solve the PD. So what we have is that in dimension n equal to 2, when the surface is like a sphere, we have difficulties in solving the differential equation. Okay, but the topology and the geometry tells us that we don't need to do that. So the partial differential equations can be solved very easily when we are below the case of the sphere, and in the case of the sphere, by topological classifications. Okay, we can conclude that we don't need to solve it, and we have the solution. We will always have the constant curvature case. Okay, so it turns out that in dimension n equal to 2, this is again a very special property of 2 dimensions, that for every metric, for any point on a given on the surface with the metric G, you can always find a metric which is conformal to this G locally, so around each point. That will change depending on the point, which is flat. Flat means that you can kind of map it to Euclidean space, and the Euclidean space being flat. So this mapping, this is such that the metric, you can change it conformally, and this will be a flat. So locally at each point we can find new metrics which is going to be flat. Globally we might not do it, but locally we can do it. And this is also called the existence of isothermal coordinates on surface. But this is in general no more true for a higher dimension, and this can again be thought as the cause of many of the problems. Okay, so this is a very specific nature of the 2-dimensional surfaces in higher dimension manifolds which satisfy this property, that at each point, if you can find a new coordinate system for which the curvature tensor is 0, that means it's flat, then such manifolds are called the conformally flat manifolds. So they have a special name. So more precisely, a manifold MG of any dimension is said to be conformally flat if for every point we can find a neighborhood of that point such that this under the conformal change, this new metric G tilde is flat. That is, the Riemann curvature tensor vanishes. Okay. So I'll see a couple of more lines and then we'll move to higher dimensions. So we see that in the analysis of the Imabe problem in 2 dimensions, this is not anyway called the Imabe problem. This doesn't have a very special name. This is called the Conformal theorem. Okay, I'm just calling it just for the sake of uniformity. So we have the following situations. Okay, so we have either the case of the metric, the total scalar curvature, the integral of the scalar curvature is non-positive, which will correspond to the non-positive invariant at higher dimension, is rather easy to solve by variational method. Okay, as we have seen. But when this is positive, which will be the case of the sphere, for sphere it is positive, and if it is positive, it's more or less going to be like a sphere, then it's not so easy. It will require some more work. So I will describe it by variational method, but later on, 90 especially, there were works by Struve and Ye they considered something analogous to the Ricci flow, but much simpler. Okay, you just change it conformally, so there's something called the Imabe flow. But in the positive case, so when the scalar curvature is positive, the techniques will not work as we have seen in the standard sphere. Okay, but in 2 dimension, because of the topological classification, isolating the sphere from the manifold is simple. It's the only one which has this number equal to 2, for which our analytic arguments break down. But for higher dimension, this is not so easy because you don't have any classification like this. So isolating the manifolds, the sphere from other manifolds is one of the major difficulties in the resolution of our problem. And now it's done. That's our next task. Okay, so I think I'll stop for maybe 5 minutes.
Yes.
So if anyone has questions, anything?
Any questions, sir?
Participants, please ask if you have any queries.
Sir, there is one question from the Karunapalli. In complex manifold, whether the same result exists or not?
Okay, in complex cases, the question is slightly different. Okay, so in general, the answer it's a difficult problem. It's called the CR Imabe problem. So again, if you're interested, you can look at any of the references I mentioned in the very beginning. Because in complex manifold, you have the special structure of the nature of the complex. You have to preserve the complex structure. So you have this extra constraint. So the more constraint you add, the problem is more difficult. So it's a perfectly good question on complex manifold, and the answers are still not complete.
Okay, sir. Thank you, sir.
If you just
any more question?
Yeah.
Any more question from audience? So, okay, sir. I think there is no more question.
Okay.
So, shall we stop for the 5 minutes?
Yeah. So we can stop for another 5 minutes and then we'll start.
And if possible,
Okay, sir. Thank you.
increase the volume. I think it is very low.
Oh, my volume is very low?
Yes.
Oh, okay, so let me know. So let me check. Maybe I'll try to speak closer to the computer.
Yes, 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 sir. That will work.
Yeah.
Someone is asking about Amave problems exist in complex manifold or not.
Yes, yes, it exists. If you just consider it as it is, so you know this is the Yamabe problem. But for complex cases, this is called the CR Yamabe problem. CR comes from the Cauchy-Riemann.
Yeah.
Also, you have something for similar when you consider manifolds with the boundary, and it's called the Escobar problem or the Cherier problem. Also for complete like non-compact cases, just complete manifolds. Shall I start or wait for a few more minutes?
Yes, I think we can resume.
Okay. So now let me, as I said, yeah, in the higher dimensions. So the curvature is a more complex object to study because it's in general a tensor. Okay, you can either consider it as a 3-1 tensor or a 4-0 tensor, but there is a very nice algebraic decomposition of curvature tensors, and it kind of tells you the various terms and how it interacts. Okay, so let me very briefly describe it. So again, let's take a manifold Mg with dimension n bigger than equal to 3. Some in some of the special cases, like dimension n equal to 3, some of the results are a little bit different. So one needs to be careful. But I'll just, for the we want to describe it very briefly, so I'll not mention the special cases. Okay. So the Riemann curvature tensor has a very nice decomposition and splitting. Okay, so you can write the Riemann curvature tensor as this quantity, which is called the Weil curvature tensor, plus some other quantities. So this is the metric, and I'll very indicate to say what is meaning by this dot here, and times PG. Okay. So this while kind of tells me that whether the manifold is conformally flat or not, and this PG, which is called the Schouten tensor, the Ricci-Schouten tensor, will tell us the deviation from being in some sense the being flat. Okay, and it's the formula for the Weil-Schouten tensor is the Schouten tensor is Ricci minus scalar times the metric G. Okay, or you can write a much more maybe a much nicer looking orthogonal splitting of the Riemann curvature tensor as to y. Okay, so this tells me whether this is conformally flat or not. Then the Einstein. Okay, Einstein, as I described, tells us whether it's the Ricci is proportional to metric or not. And then this is the other part. Okay, the corresponding the leftward part. So EG is called the Einstein curvature tensor, or the Ricci, the traceless Ricci, because if you take the trace, this is going to vanish. Okay, and this dot product has a very special name. It's called the Kulkarni-Mitsu product. So Kulkarni. And you can, it's a tensor product, symmetric tensor product, and this is described as here. This is very useful for writing the decomposition. So why I wrote something like this, what is the use of writing a complicated formula? This is because of this particular reason. For dimension n bigger than equal to 4, so dimension equal to 3 is something different. You have this something called the Barth tensor, the Cotton tensor. So manifold is conformally flat if and only if the while is 0, the while curvature is 0. So if the while curvature is 0, the while curvature measures whether the manifold is conformally flat or not. So it is conformally flat if and only if the while curvature is 0, and the while curvature is furthermore a conformally invariant quantity. So if you change the metric from g to g tilde given by exponential of 2u, the while also changes in the same way. So any two, being conformally flat doesn't depend, only depends on the conformal class. So if you take any two metrics in the conformal class, if it is if the while is 0 with respect to the one, so it's going to be 0 with respect to the other also. So this is a very nice, a very useful orthogonal splitting of the curvature tensors. Okay. So coming back to this Yamabe problem, which is finding constant scalar curvature metrics for dimension bigger than or equal to 3. So the question we're asking now is it possible to find metrics with constant scalar curvature only in higher dimensions? Okay, so as I described earlier, so if you change the metric from g to g tilde by this conformal factor of u to the power 4 by n minus 2, and the reason why we write like this is it gives us a very nice looking equation. So the conformal transformations are related by this formula. So which is basically here. This is the conformal Laplacian. On the right hand side is some u to some particular polynomial power times this the curvature of the scalar curvature with respect to this new metric. So as in the case of the two dimensions, so to prove that there is a metric g tilde conformal to G of constant scalar curvature is then equivalent to proving that there exists a lambda. Okay, so you want this to be constant lambda, and a positive smooth solution to this equation. So which is Laplacian of u plus this dimensional constant times SGU is equal to lambda times u to some power, or the conformal Laplacian is equal to the right hand side. Okay, so in some sense, we have the similar looking equations which we want to solve, and the nature of the difficulties are going to be similar. Okay, just the non-linearities are a little bit different. Okay. So in dimension n bigger than or equal to 3, so we write the conformal class as box G, which in this case is changes by u to power 4 by n minus 4 divided by n minus 2 times G, where u is smooth and positive. Okay, so what Yamabe observed was that in 1960s that to find the solutions of this equation, okay, you can just consider the critical points of the Yamabe functional, which is just the Hilbert functional, restricted to the conformal class. So you don't, in some sense, you have a functional, and in Rn, you can consider it in high dimensions, and then you don't move in every direction, you just move in the conformal direction, if we just change it conformally. So then this is the Yamabe functional, and the critical points of this Yamabe functional will give you the solutions of the Yamabe equation. Okay, and then you would have solved the problem completely. Okay, and this was his observation in 1960s, and he concluded that yes, you can do it. Okay, but it turned out to be not so correct. Okay, so the Yamabe, this is the Yamabe functional. So you want to find the critical points of functional. So as a very first approach, you will look for the minimizers. So the Yamabe invariant of the manifold Mg. So M is the background metric, background manifold, and G is the as a metric on it. So we fix a metric G. So YMG. So this is the infimum of this functional. So if you have this infimum, and this because we are looking for the minimizer, so we look for the infimum. And if this infimum exists and there is something, some function which achieves the infimum, then that will be the critical point, and we'd have to find the solution of the Yamabe equation. So that was this goal. Okay. So he wrote this infimum, and now it's called the Yamabe invariant of the manifold, and it's a geometric quantity. Okay, the Yamabe invariant is that this is the total scalar curvature normalized by the volume. So if you consider manifolds with volume equal to 1, you don't have to consider this, but otherwise you have to normalize it suitably to dimensions, and then you consider the infimum, but the infimum is taken with the conformal class only. Okay. So the Yamabe invariant is, first of all, by this very nature of the definition, we are considering the infimum over a fixed conformal class. So it's obviously, if you pick any two G tildes in the same conformal class, is going to be the same. So it's by the very definition, it's a conformal invariant quantity, and the numerical value, okay, in some sense, or this value you can very easily compute it, is going to be central to the analysis of the Yamabe problem. So very roughly, you have these three normalizations, classifications. In some sense, the Yamabe the Yamabe invariant of the manifold class kind of breaks the manifold into three classes. So you fix the metric G and you consider this conformal class. So if the Yamabe invariant is negative, then essentially that means that you can find a metric in the conformal class for which the scalar curvature is always negative. If it is zero, you can always find conformal metrics such that the scalar curvature is always zero. Or and if it is positive, that is equivalent to saying that you can always find a conformal matrix for which the scalar curvature is always positive. So as you might or might not know, the manifolds having negative scalar curvature, non-positive scalar curvature, in some sense generic, you can always not conformally. Okay, even if not conformally, you can always give a metric for which the scalar curvature is going to be negative. But there is some topological obstructions to manifolds having positive scalar curvature. This kind of gives some information on the topology. So this is not always an easy task to do, but Yamabe solves it conformally. So looking from functional viewpoint, so because of the nature of the conformal transformations, so Yamabe kind of realized that equivalently you can find the define the Yamabe invariant as the infimum of quotient, okay, quotient where the numerator is u, phi, some function phi times the conformal Laplacian acting on phi, okay. And then in the denominator, because of the volume, you have this corresponding factor, phi to the power 2n by minus 2, and then you normalize it. So this is the same, the total scalar curvature normalized with respect to the volume is the same as this particular definition, where we just consider this conformal factors as functions phi. Okay. So because sometimes it's much more easier to work with, especially if you're looking to understand it from a PD viewpoint. So Yamabe equation, then solving the Yamabe equation is amounts to finding critical points of this function now. So you take an appropriate space of functions, which I'm not going to describe, and you just find the critical points of that of this corresponding function, this function on the space of this corresponding spaces of functions. Okay. So a function on the space of functions. So you just look for infimum and hopefully more critical points. Okay. So let us describe the bad case, as you kind of suspect that happened for the two-dimension case for the sphere. So in this sphere, in some sense, we don't need to solve the equation, but if a manifold is not like a sphere, sense of the Yamabe invariant, it's easy to solve from the viewpoint of partial differential. But this is again the same theme. So on the sphere, so you can write the Yamabe equation as this. So G STD is the standard round metric on the sphere, which it kind of gets from being embedded in Rn plus 1. Okay. So on the standard sphere, the standard round metric is a metric with constant scalar curvature, has a constant scalar curvature, and you can compute it and show that it's equal to n times n minus 1. Okay, so now the question you can ask me is, are these the only metrics on the sphere which is conformal to the standard matrix for which the scalar curvature is going to be constant? The answer is yes. So this is the work of Obata, Oba and Talenti. So that that this standard round matrix is the metric, okay, which minimizes the Yamabe functional, and the constant multiples of this standard round matrix or its images by conformal deformations are the only solutions of the Yamabe problem on the sphere, or it minimizes the Yamabe function on the sphere. So this was this is kind of a very nice picture that happens on the sphere. So in the sphere you have you have a lot of solutions to these kind of equations. Okay, so in some sense, from the geometric viewpoint, you don't need to solve it because it already has constant scalar curvature, and any metric which is going to be conformal to it is going to be again have constant scalar curvature. And then okay, and so but looking from the other direction, you can completely classify it. So for the standard sphere, its conformal diffeomorphisms are going to be the ones which have constant scalar curvatures, and all those constant conformal diffeomorphisms, the conformal factor will solve this equation. So you have, in some sense, infinitely many solutions to this equation on the sphere. But this is a cause of huge problem from the analysis report. Okay. So again, looking from the case of the sphere, so here I wish I could have drawn some pictures. So the Yamabe, as I mentioned, the Yamabe function on the sphere is minimized by the standard round matrix and its multiples and its conformal transformation, and these are the only ones. So, okay, one way to look at the picture on the sphere is to consider the stereographic projection. So you take the sphere, you take the north pole, and you consider the stereographic projection. So which is for any point on the sphere except the north pole, you consider the line connecting that point to the north pole and see where it intersects the plane. So that is the image, okay, in Rn. So, but you can describe it, write it as a formula in this way. And this is a conformal transformation. So sphere, this is also called the compactification, one-point compactification of the plane, or Rn. So sphere minus a point is conformal to your Rn. So this allows us to transfer equations from the sphere to the Euclidean case, or equivalently the equations on Rn to sphere. Okay. So and this phi, this stereographic projection, is a conformal transformation, and the pullback of this is on the standard round metric has this conformal factor. The conformal factor looks like 4 divided by 1 plus distance squared, the whole thing squared, and this is my notation for the Euclidean metric. Okay, so what is the use of this? So because there is a very classical theorem of Liouville that kind of classifies all the conformal transformation of the Euclidean spaces, that it's going to be only translations, rotation, or dilation. You can change the scale. Okay, you can translate it, you can rotate it, you can take the inversions. Okay, and these are the only kind of conformal transformations of Rn. So by this stereographic projection, by pulling it back, these are the only ones, only conformal transformations of the standard round sphere. And so you can explicitly write the solutions of the Yamabe problem on the sphere, okay, and you get infinitely many of them. So if you have the conformal transformation phi from a conformal diffeomorphism to sphere to itself, then obviously you can rotate it. Okay, so because of that, so let's consider, so you take the stereographic projection. So first you pull it down to the Euclidean space. Sorry, from the Euclidean space you push it back to the sphere space. You apply this conformal diffeomorphism and you pull it down to the Euclidean case. Then one has this. Okay, because of the classification of the conformal transformation on the Euclidean space, we have this classification on the sphere that is going to be rotation, compositions, or rotations, translations, or dilations. Okay, so and using this, you can explicitly write down the solutions of the Yamabe problem on the sphere. And so, just by taking rotations or translations or dilations, you can realize that there are infinitely many of them. So, in some sense, the sphere has infinitely many solutions. So, what was the mistake of Yamabe was that, so in some sense, you have this infimum, and you consider a minimizing sequence. So, if you consider the case of the sphere, you have again the infimum, and if you consider minimizing sequence, you cannot guarantee that it's going to converge. So, there is no compactness in some sense to the solutions of the Yamabe problem on the sphere. Because of this, you can just translate, and by translating you can go into infinity. You can just dilate, you can concentrate at one point, and so on. So you don't have this in general the compactness. So minimizing sequence might not converge. So it can blow up. It can at some point become very large, infinity, and that breaks down the whole theory. And what Yamabe kind of his mistake was that he assumed that these minimizing sequences are always convergent up to a subsequence, but this is not true in general. So Yamabe, he kind of approves this problem using, this is called the method of the calculus of variations or elliptic. So this was the assumption in 68. So there is a very nice division of time, 8 years apart. So 68, Neil Turinger he kind of found the flaw in the Yamabe's proof, and he kind of also was able to repair the Yamabe problem solution when the Yamabe invariant is kind of is not very close to the sphere. Okay, so, in particular, it's not non-positive. Okay. So one can very easily show that the Yamabe invariant is always bounded by the Yamabe invariant of the standard round sphere for any manifold M and any metric G. Okay, and why is that this case? Because if you just take, I have the computation, so hopefully I'll be able to show it. Okay. So you take the manifold, you just look at one particular point, and you construct basically, you attach a sphere at that point. Okay. So you're basically taking the infimums, and you always, in some sense, get this trivial, this inequality is not very difficult to establish. Okay. What Oba realized was that, so this is where your concentration kind of phenomena picture comes up, development analysis comes up. So Oba kind of realized in 8 years later, in 74, that the Yamabe problem, you can solve it, provided you are below the case of the sphere. So remember, what happened in 2 dimension was that, so if your Euler-Poincare characteristic was strictly below that of the sphere, then you can solve it. So same thing happens here analytically. So if you're below the case of the sphere, in this case, this is described by the Yamabe invariant, you can solve it analytically. Okay. So as long, in some sense, the manifold doesn't develop a sphere, doesn't have a sphere glued to it, okay, locally at some point doesn't look like a sphere, you can solve it. Okay. Okay, so this was the first discovery of Oba, and this is a very common theme nowadays in geometrical analysis. In geometrical analysis, you'll find that this canonical classification always happens, that if you're always below some critical parameter, you can solve these equations, and that critical parameter encodes the geometry of the problem. Okay. So, we need to basically better understand what this Yamabe invariant is, which is a conformal invariant quantity for any given manifold. And the question now, what can kind of transfer is that, so from solving equations, we just come to establishing an inequality. That can we always establish this inequality that for any given manifold, is this always true, provided it's not a sphere. So if it's a sphere, of course this is an equality. But for the sphere, by the previous couple of slides, I told you that we have solved the solution. We have infinitely many solutions, so we don't have to bother about that. But if your manifold is not like a sphere, can we solve it? So this is the question. So can we establish this inequality? The answer is yes. And that requires some serious work by Oba and Shen. Okay. So Yamabe kind of proposed this problem, and then in 74, kind of Oba kind of gave a condition, analytical condition, that the Yamabe invariant is strictly below the Yamabe invariant of the sphere, standard round sphere. Then you can solve this equation. Okay. Okay. So what you can do is that you have this going back to the definition. So if you can find one function, right, you have to find just one function for which this quantity is strictly below the sphere. Okay, so that function is called the test function. Then it would be done. So your whole job is to find one function. So maybe you can start with taking the constant function, but it will not work obviously. But there is also very nice work by Jost and others in that direction. So if you can find one function, that the whole problem boiled down to constructing appropriate test functions, okay, for which you can establish the inequality, whether you can do it or not also. So in 1976, again, okay, as I said, 60, then 68, and then 76, Oba proved the first positive result in this direction. Okay, and he was able to find a test function, but this was local. Okay, I'll kind of tell you why it is local and what is meant by being local. So basically, you take a point, you consider a test function. You just take the compactly supported test function around the neighborhood of that point, and then you plug it here and see what happens. You expand it, and then some geometrical terms, some geometry of the manifold will pop out, and he was able to show that in certain cases that if the dimension is bigger than or equal to 6, or if the manifold is not locally conformally flat, then you can it is if it is bigger than or equal to 6 and it's also not locally conformally flat, then you can have this strict inequality and then you would have solved the problem. So from the PD viewpoint, so the Oba test functions, so how does the test function? So constants are not going to work. So what explicit functions we know? So we know the solutions of the Yamabe problem in the sphere. So what Oba did was consider the solutions of the Yamabe problem in the sphere, for which you can write it explicitly and then just pull it back on the manifold, because everything we are doing it locally, you can do it in a proper way and expand it. But looking from the Euclidean viewpoint, and if you know some PD theory, so these are the extremal functions of the Euclidean Sobolev inequality. We should just pull it back on the manifold and expand. So I have a couple of slides in that direction. Okay, so what you do is that so you take a point xi, okay, and you take the smooth cutoff function so that everything is well defined around that point, and then around for epsilon is a parameter, and up to this parameter you consider this localized test functions. So this kind of tells you that this is kind of defined globally in the manifold, and outside big radius from xi, large enough distances from this point, fixed point xi, this is 0. So you have this epsilon by epsilon squared by this distance squared, that whole thing n minus 2 by 2. Okay, and then you can kind of rescale and rewrite it as in terms of the single function u. And this function u is not arbitrary. It's one of the most significant functions, especially from the Yamabe viewpoint in PD theory, that this u are the solutions of the Yamabe problem on the sphere. Okay, or you can pull it back, by stereophoric projection. This is equivalent to solving it on Rn on the Euclidean space. So these are the only solutions of the classified by Oba, Talenti, and Obata, that this satisfies this equation in Rn. Okay, so you have the solutions in Rn by Obata, Talenti, and Obata, or on the sphere. You use those solutions for which you know explicitly. Okay, and then you kind of attach it, glue it on the manifold, and expand it, and you look at what happens as the manifold. Okay, so this is your functional. Okay, so now I'll just kind of very briefly, this is a very useful calculation. It's mentioned in this article by Lee Parker. So using this conformal novel coordinates, as I said that, the volume form has 1 minus the scalar curvature and Ricci and so on. But because it's a conformal problem, you can find good enough coordinates by only considering conformal changes, and for which is going to be equal to 1, precisely 1. So this is a very, very nice technical thing, and it's there in this very nice article by Lee and Parker. And in this conformal coordinates, the calculation becomes extremely quite not very simple, but simple enough, as simple as Euclidean ones. So because the scalar curvatures are going to vanish, the derivative of the scalar will vanish, and then the Laplacian of the scalar will give you the wild curvature. So here you can see the connection between the scalar curvature and the wild curvature. The Ricci is going to vanish at that particular point, and the symmetrized derivatives of Ricci are also going to vanish. So if you do the expansion, and so where the geometry comes out is as follows. So the first term is the Yamabe unit of the sphere. This is to be expected because you are taking the functions which achieves the values on the sphere and you expand it. So up to 0 other term, this is going to be exactly that, and then up to some so epsilon to some sufficient. This power may not be exactly right, but up to some power. So you have these corresponding terms where the wild curvature comes because of you have the scalar Laplacian of the scalar curvature. So this should be n bigger than 6, strictly bigger than 6. So you have the wild square. So if this is positive, so, okay, this can be only 0 or positive. If this is positive, so you have a negative sign in front. Okay, and the ck is a positive constant, so you're below the Yamabe invariant of the sphere, and you have solved it. So if this is positive, means that the manifold is not conformally flat around this point. So you have solved it. So that's how the Oba solved the problem in the case of high dimensions and manifolds being not conformally flat. Okay, so this was all going on very well, but still the full resolution was still not there, and then that required a very unexpected twist coming from general relativity and the positive mass theorem and Shen and Yang. So I'll stop with that. So it remains to prove that this inequality is still valid for remaining dimensions 3, 4, and 5. And when the manifold is conformally flat, if it is conformally flat, how much more can we distinguish it from it being a sphere? Sphere is also conformally flat. Okay. So when it's like a conformal flat, then from local conformal viewpoint, it's like a sphere. So if you do the test function expansion, this is 0, and we are not getting a strip inequality, right? So in this case, the Omar test function breakdown, and the global, in some sense, some more geometry of the manifold has to be somehow taken into the consideration. So the final resolution of the Omar problem is due to Richard Shen in 1984, again 8 years apart. So the proof was very significant and very unexpected. So he recognized the relevance of the positive mass theorem of general relativity, which from analytical and PD viewpoint is kind of tells you information on the Green's function of the role of the Green's function of the conformal Laplacian. So if you denote the Green's function of the conformal Laplacian, so which if you know from the theory of differential equation is the Green's function basically means that it solves the equation conformal Laplacian equal to Dirac delta. So at one point it becomes infinity, at everywhere else it's equal to 0. Okay. So then you can expand it. So then you need to find the explicit value of this Green's function. So for dimension n equal to 3, 4, 5 are locally conformally flat. So this is expansion is given like this. So again, this is exactly like what happens in the Euclidean case. You have the distance to the power n minus 2. Okay, and then you have the remaining term. So this is a smooth, nice function. Okay, and okay, and why it is called mass is that because there is a long-standing conjecture in general relativity. If you kind of puncture your manifold and consider like the generalization of the stereographic projection by considering asymptotically flat manifold. So the universe, consider a model of the universe where initially you have some mass. Initially it can look like a lump, and then later on for future times, as you go very far from the mass, it's kind of flat. So this is how you can model it by taking the conformal factor where given by the Green's function. Okay, so this term at that point, so m xi is going to be the mass at that point. So the conjecture, I don't know much of general relativity, but the conjecture was that the mass is positive, and it was a long-standing conjecture for a very long time. So Shen and Yao was able to prove it independently and apply it here for the Yamabe problem. So this turns out to be called the mass of the asymptotically flat manifold. Okay, so this is in the physics literature. You know, as you can maybe you can see some of these references. So this is the mass of the asymptotically flat manifold. So more precise with non-negative scalar curvature, and because you have to because it's an asymptotically flat manifold, the volume is infinite. So to make sense of it, the scalar curvature has to be integrable. Is the conjecture is non-negative and is 0 if and only if it's the Euclidean. So Euclidean has if it is isometric to the Euclidean space with same dimensions. The Euclidean manifolds have 0 mass, so the only 0 mass manifolds are isometric to the Euclidean. So this is the strong form of the positive mass conjecture. It was solved by Shen and Yao, as I mentioned, in early 80s or late 70s, by using minimal surface techniques, and later on, I think it's still now people accept it to be solved for dimension only till 7. For in general, it's still kind of not clear that whether it's solved or not. But Edward Witten was able to solve it in a general case, but only when you have some more extra spin structure. But the general case is kind of okay. But for us, the Imabe problem, we don't need it in full generality. The weak form tells us that the mass is non-negative, so it should be a non-negative quantity, and it is 0 if and only if the manifold is conformally diffeomorphic to the unit sphere. We don't need it to be isometric. We don't just need it conformally diffeomorphic to the unit sphere of the same dimension. And this was proved by Shen and Yao for all dimensions. And this is what is going to be used. So again, in the what they did was, so what Shen did was for the remaining cases in low dimensions or for conformally flat cases. So he considered appropriate test functions, and that test function encodes this mass function. Okay, and again does the same kind of expansion, and then this kind of terms pop up. So here you can see the mass function here. Okay, So this mass function, if it is positive, then you can again go below the level of the sphere, and then you have the strict inequality, and then you have the solution. And but this is always positive unless the manifold is like conformally equivalent to the standard round sphere. And so we have basically solved it unless it's a conformally equivalent to the standard round sphere, for which we don't need to solve it. So this is the final resolution of the MOI problem, that for bigger dimensions, for all dimension n bigger than equal to 3, this inequality was established independently by two different techniques and two complementary techniques. Okay, and so this is a strict inequality unless the manifold is like a sphere, so that is conformally diffeomorphic to the sphere. And in particular, you always have a minimizing solution, and the MOI problem is solved. So I guess this is, I'll stop. Okay, and stop for questions.
Sir, thank you very much. Any questions and comment?
You can put in chat box also.
So I think
provide some references. Hello.
Hello.
I'm just asking for the participants' benefit, if you can provide some references to read these type of
References, yeah, sure, absolutely. I mentioned it at the very beginning. So yeah, so some references, as I mentioned, you can always go back and refer to this significant book by Obama called Some Nonlinear Problems in Remaining Geometry. Or you can also, for the, in particular for the MOI problem, this is the definitive article by Lee Parker, okay, called the MOI problem, published in late 90s. This very nice, short book by Alice Chang called Nonlinear Elliptic Equations in Conformal Geometry, and in particular discusses the MOI problem and the problem of prescribing curvatures. Okay, from the viewpoint of block analysis and PD theory. So this survey article by Olivier Drouet and Emmanuel Levy called Elliptic Equations in MOI type is also very nice. And then you have this very nice and now classical book called the Lectures on Differential Geometry by Shen and Yao. Okay. And then of course you have this delightful read by Arthur Bess called the Einstein Manifolds. These are my typical references.
I think Renu has raised hand. So you may ask.
Renu, have you any question? Renu?
So, sir, I think we should conclude.
Yes. And Dr. Majumdar, if possible, please share this slide.
Yeah, I will send it to you.
Yes, so that we can share with participants.
Sure.
There are so many newcomers and they can plan their research in these areas.
I'll share these slides.
Okay, so
okay, sir. I think there is no question and comments. So,
yes.
So Professor Majumdar, we are very thankful to you for providing us time for this lecture, and we are very thankful to giving some insight of the MOI problem. So I think this service should discontinue.
Yes, yes. On behalf of organizers, I am also very thankful to Dr. Majumdar that he accepted our invitation and given his time and share his thoughts with participants. And it was quite a nice presentation. And I am sure that the participants will be benefited a lot. Thank you, Dr. Sir.
Thank you so
Thank you, sir.
much. Thank you so much.
Okay,
Thank
so
you.
this we will conclude this session, and the participants please join tomorrow in morning at 11 o'clock for Professor M. Prabhakar lecture. Okay, thanks.
Thank you. Thank you all.
Thank you, sir.